This is the ROS Developers Podcast, episode 83.
The ROS Developers Podcast. The ROS Developers. The ROS Developers Podcast. The ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that give you insights from the experts about how to program your robots with ROS. This is Ricardo Tellez from The Construct, and today I would like to dedicate this episode to all those ROS developers around there that you are working on creating all your control algorithms for your humanoid robots. So you know how difficult that is and how challenging it is, especially because you have to take into account the real-time control. Otherwise, your robot is going to fall down, right? Then if you are one of those that are working on this subject, this episode is dedicated to you. Now, why is that dedication? Because today we have a very special guest with who we are going to talk about how to achieve real-time control under ROS. That's a very cool subject and difficult one. So let's go to that. But before starting with the subject, let me remind you about our online academy for learning ROS, which is called the Robot Ignite Academy. And you know about that academy, right? We have many different courses based on practice on simulated robots. You know that, right? So we are showing you a web interface where you can see the lessons and all the exercises that you have to do on the site and apply to the simulated robot already provided. You need to do no installation at all, and then it's working smoothly in any computer, any operating system, and so on. Try it because we have courses starting from the novice, the one that doesn't know anything about ROS or even programming, and for the experts in subjects like deep learning, robot manipulation, navigation, etc. Have a look at the show notes, okay? I will leave a link for you to have a look at the academy. And now, let me introduce you the guest of today. So today we are going to have a talk with Luca Marchionni. And so what can I say about Luca? Luca and I, we have been working together for 5 years plus at Pal Robotics. And we were designing together navigation algorithms for the humanoid robots of the company. Some of them, previous versions of the ones that you can see there on the screen, that's the new robot that they have built recently. It's called ARI, and it's a humanoid with a mobile platform on the base, but with human embodiment and also movement and so on. Very, very cool. So we started to work together on those algorithms, but then Luca started to work on other problems of control of closed loop systems, and then applying all these to whole body control, walking of humanoids with legs, so leg humanoid robots, human size, I have to say here. So it's not a small humanoids, but human size humanoid robots with legs, and also apply this to motion planning and control to all those human-sized humanoid robots that are built at Pal Robotics. And for that specific thing, so Luca had to develop some algorithms with real-time control using ROS. That's why he is here today. And now Luca, he has progressed a lot, and he is now the CTO of Pal Robotics, and he's in charge of the technical vision of the company. Welcome to the podcast, Luca.
Thank you, Ricardo, for the introduction. And hi, everybody. It's a pleasure to be here with you.
Yeah, second time, right?
Yeah.
Actually, Luca, you were the first person that interviewed in the podcast. You are on episode 1.
Oh, nice.
Yeah, which is one about humanoid robots with ROS, and it's one of the most successful ones. It's one of the top 10.
Nice.
even if it is the first one, right? That so few people knew at that time. And okay, so I have a series of questions, but I want to start with another one, special for you. So, what is more difficult, to build control algorithms with real time for humanoids, or to manage your life with your two childs?
It's comparable, the difficulty. Eh?
Is
So,
it right?
yeah, yeah. You need to control everything. I also with the families, it's complicated, especially with young children that are really active and then they want to, I mean, always play or cry or whatever. So it's continuous negotiation, both in during the work, but also outside.
And in real time, right?
Exactly, and multiple tasks. Yeah, so
And
it's
multiple tasks. Multitasking. Great. Then I wanted to ask you first if you can define what is real-time control.
okay. In real-time control, it's normally associated to a control system that is able to deliver on time commands or computation. Yeah, so it's meant for a system that needs some time of determinism, some type of let's say continuous throughput in a specific time interval. So that time interval should be respected as much as possible, so to reduce the variability of the output depending on the condition, on the load, or on the type of inputs of the system. And this is quite important in many applications, especially in robotics, because we want to have robots that are, let's say, predictable. We want to have robots that are safe, so that you can ensure the smoothness of a motion of a manipulator by controlling periodically the commands and reading periodically the measurement from the sensor of the robot to process them and then compute the next command. Yeah.
Exactly.
So it's really tightly coupled with whatever we are used to treat in robotics in terms of responsiveness of the system, smoothness of the motion, and stability of a system. Imagine that normally in control theory, as we use digital computers for controlling the robots, we have some kind of, let's say, limitation that are defined by the frequency we use for controlling the robot. So there is the famous Shannon theorem that say that we cannot control a system that is much faster than the frequency that we can control it.
Okay.
Yeah?
Yeah.
So there is a limitation in the performance that we can achieve depending on the frequency of the control. So to say that normally is confused real time with frequency of control. We can have a real time system that is slow, but is really precise in getting the right command at the right time. But then normally when we have complex system that requires high frequency of control, real time is even more important, because then it's not easy to respect this time constraint.
Yeah.
So it's called jitter. So the variability in the output of the commands, the time output variability is called jitter. So real time control system has really low jitter and ensure high precision in providing this type of output commands and computation.
Okay, yeah. So just to give an example of what happens if you need real-time control with an armed robot and you don't respect that, then you can get movements that are not smooth because like that are like doing like this and then going back and then doing something like that is not smooth.
Or even if you don't have real time, you can have missynchronization between the different joints of the robot. So you are supposed to move along a line, the end effector, but at the end you are moving, I know, on a curve.
Exactly.
Because the control is not sent at the right time to the right joints.
Exactly, and that's even worse when you are applying this to a humanoid robot on the walking, right? Because by not respecting this, you can make the robot fall down, even if your algorithm is properly is correct and providing the proper gate
Yeah,
of
because
the
in many systems, also having the right answer, but at the wrong time is a,
exactly,
is a failure. It's a
exactly.
failure. Yeah.
Uh,
So in real-time system, you have this that is you need to have the answer in the right at the right time window.
Exactly.
Otherwise, your system can behave unexpectedly. Okay? The system can crash, the robot can fall, you can damage something or make hurt someone. Yeah?
Okay. Yeah, and I also like what you mentioned about the that having real time doesn't mean a fast system. That you can have a real time compliant algorithm which is going in a slow frequency, but it's more important to have real time when you need it when it's a high frequency because it's more difficult, right? And then you miss more steps of the control, right? I like that thing, and so that's so we have. I had another question about that. I already answered. So, do the next question for me is: do we need real time for all robots?
I would say yes, at least the one that I'm used to work with. So even mobile bases, which only two motors maybe for the wheels, you may need real time because you want to have I know the robot moving straight when you command the wheels with a certain speed, or you want to have some kind of even as I said before reactive behavior, so that if you control the robot to stop,
Yeah.
you want to have some guarantees that that command reaches the wheels in a certain amount of time. So imagining that if you want to brake and you have to decelerate the robot, you need to have a certain frequency of this command to reach the wheels to have a smooth deceleration. Yeah.
Exactly.
And so to have this braking distance in some sense predictable and that the algorithm then can take into account to I know, limit the maximum velocity or
Yeah.
interpreting the distance sensors in the correct way. So
Yes.
in our company, um, we have, I mean, from mobile bases, we use already real-time system, but then when the robot get more complex or more degrees of freedom and manipulators or humanoid robots, that becomes even more important.
Uh-huh.
So I would say yes.
Yes.
Then especially is more important when you have also in communication in between. So in which not only the computer should perform some computation, so in executing an algorithm, but then you have to communicate the result to someone else.
Uh-huh.
So, for instance, if you have electronic boards that are controlling the motor that are decentralized or are placed somewhere else in the robot structure,
Uh-huh.
or if you have sensors that are somewhere else, you want to have real-time communication or real-time control over these sensor and actuators.
Yeah,
Yeah.
because then you have the proper synchronization, right, between one thing, what you are sensing and what you are actuating on, right? Yeah, so that's a very good point. I've never thought about putting real time in a mobile base because so the mobile base they are stable by themselves, and then if you are moving around and you need to brake to stop suddenly because something unexpected happened, then you can do that by measuring the amount of time that you are going to need as to based on the physics of the mobile base, and then knowing that you cannot ensure real time, so you can expect, oh, so I'm going to have as much as this delay, so I will need this extra time in the worst situation, and then I can plan in this way. So for the mobile bases, because usually they don't move very fast, so that's not making the difference. But
Sure.
if you want to polish and then to have your mobile base that goes at the maximum speed that it can go and be fine-tuned exactly, then put in real time even on mobile bases, then it's going to be a big increase in the capabilities of that
But
mobile.
especially imagine that if the problem is that still the autonomous navigation is not yet let's say, deployed in a real commercial product like autonomous car. So if they have to certify the navigation stack of an autonomous car, you need to ensure that if a sensor detects an obstacle, you have, I don't know how many cycle time before that sensor reading is processed and before that sensor is contribute to the output command that is sent to the wheels of the car. So without determinism and without a system that is predictable, it's really difficult to certify safety.
Yes.
Yeah.
Yeah, because you are.
Even for as you said before, even for an algorithm that is correct, in this, let's say, safe critical application, you need to take into account also the execution time, the periodic execution of your algorithm, and the effect of this on the possible outcome. Because otherwise, every time, depending on the system load or depending on the time window in which the algorithm enters the output command, you will have different.
Exactly. Very well put. Yeah, and these is such a complex system like the autonomous car that you mentioned. That is not only one system. Is this system, this other. So all of them they are adding here. So it's becoming very complex to certify. Just by putting this real time constraint, you can certify the whole system by certifying each one of the parts. Okay, and then so you kind of answer the next question, but at Pal Robotics, you have several types of robots. For example, the ones that you have over there, the human ARI robot, that are humanoid robots. For those who are listening and not watching the video, then those are human-sized humanoid robots, but those have a torso with head and arms, and so a touch screen on the chest. And also there is a mobile base on the instead of legs, so that's making them more stable. And then you have other different robots. You have a couple of different types of ledge humanoid robots, the Talos and the Rim C.
Yes, and we are designing a new one.
Oh, okay. So wait. Let's stop the machines. So these are new. So I didn't know about that. So tell us. Very interesting.
Yeah, we have a new biped on
production.
In product, not in production yet, but we have some let's say already explored some new actuation systems. So we have a new type of let's say actuators that are really promising in terms of resilience to impact and power density.
Wow.
And also the distribution of the actuators in the robot is quite new for us. So the idea is to reduce as much as possible the weight of the robot, the inertia of the moving limbs, so the legs and the arms, and to have a robust platform that can fall and can jump and can resist really stress behavior. Because one of the problems that we have with the previous generation of robot is that they need a safety crane. They are really fragile because if they fall down, they can break, and some of the sensor or actuators used can get blocked or can be damaged. So we wanted to explore a new type of actuation, a new type of structure of the robot to address this problem and to provide a much more robust platform that then researchers can use in let's say in a more useful way, in the sense that they can maximize their time on the robot and they can do really advanced mobility experiments. Yeah, while normally with the big size human-sized humanoid robot that we have so far, we are some limitation. We have some limitation in terms of the dynamic motion that you can do, because the robots are heavy. They are, let's say, complex to use because they are also
to manipulate.
Yeah, exactly.
And so then, I don't know if I have understood correctly, then this new humanoid is not going to be human size? It's going to be smaller?
For the moment, we are concentrated in a torso with lower body, so only legs and a torso.
Okay.
It's gonna be a little bit shorter than previous robots. So the idea is also that to have it more like easy to handle for
Uh-huh.
only one researcher. Yeah, so
Yes.
the target is to have it at less than 50 kilograms and about 1.5 meter.
Okay. Okay. Yeah. Because I remember managing the humanoids. It's a pain because they when you shoot it the power off, then it falls. Everything falls. So and it's heavy. So if it falls in on top of somebody, then it can hurt the person, but also it can break. So you always have to have the crane. The crane is it's very large and it's it was
Yeah,
very
it's,
nasty.
yeah, it's an additional constraint in what the robot can do because you have always to have the robot hanging. Yeah,
Yeah,
so
just in case that it falls or something goes wrong. Yeah. Okay. Okay. Nice. Do you have any date for release of this new product?
probably second quarter of next year. Now we are
Okay.
manufacturing some parts, so that the idea is to have prototype by beginning of next year, and we will have like a official launch of the robot and during next year.
Okay. Then count on the podcast for doing a press release on that also. So because the people will like to know about that. Great, great. Okay, so that's news. Remember, you hear this first here, the ROS Developers Podcast. Great. And then, uh, let's say, okay, I have my robot, and okay, wait, but you didn't answer the previous question because I didn't ask. So, which one of your robots do require real time, and which one doesn't? So you mentioned before that you would put in all of them, but actually,
Yeah.
are you doing that?
Yeah, we do that because we have
Ah, okay.
the core system of our robots is all the same. So we use let's say we try to make the core libraries and packages common
Yeah,
among all the robots.
that
Yeah,
simplifies.
yes, exactly.
Ah,
So
okay.
that is a really stable core of libraries that then we can reuse as much as possible, and they are really tested, and then it's easy then to configure or to use a new robot because the core architecture is not changing.
Uh-huh. Okay, okay. Okay, yeah, I didn't know that because when I was working there, we still didn't have this common for all the robots, and the mobile bases didn't have real time at that time. So
Yeah.
so many years ago. Okay, then so let's say I'm convinced I want to put real time on my robot. So what's the first element in the chain in order to achieve real time control?
For sure, you need to choose an operative system that is real-time capable or that offers uh, system calls and functionalities to allow your programs to be executed in a real-time way.
Okay. And can we use, for example, any operating system is able to do real time? For example, Ubuntu?
I mean, there are several operating systems that are real time. Then there is also the difference between hard real time and soft real time. So hard real time are like more industrial operating system, like QNX that are used in many really safe critical applications, like space application, nuclear plant, or more industrial medical application. But then the most used operating system is Ubuntu with some kind of patches. Yeah. So, for instance, we have been using in different version of real-time operating system, but in the last 4 or 5 years, we use Ubuntu with an RT preempt patch. So that is a soft real-time system. It's not really hard real-time as Xenomai or QNX, but offers more flexibility for the developers
Yeah.
so that it's easier to
Yeah.
to have a real time system with this type of configuration. And what this patch offers basically offers some like additional capabilities to a standard operating system. So there are different scheduler that you can select from, and some of the scheduler are, for instance, FIFO, so first in, first out, and you have guarantees that a program that is scheduled by one of these FIFO scheduler isn't preempt or interrupted by other programs that are running on non-real-time scheduler. So there is like kind of hierarchy of the scheduler that are used.
Okay.
And this then also affects, for instance, some type of systems calls. For instance, the mutex in a patched Linux system are non-blocking. And this is something that also you need to care about, because you don't want to have starvation or having some of your programs that are blocked because they are in a mutex. Yeah.
Uh-huh.
So you have some functionalities that are added with this RT preempt patch in Linux system.
Okay. Then, yeah, so you mentioned is Ubuntu with this patch, and then I
Yeah.
will put some links to that into the show notes for people who want to try. It's actually quite easy to apply those patches, so it's nothing complicated. And then you mentioned about Xenomai. I don't know if you remember at the beginning when you
Linux,
started, we were using at Pal Robotics Xenomai, and we had to
Yes.
cross-compile,
Yeah.
and then it was a it was a mess because you were developing in one system, and then you had to cross-compile, send to the robot, and then there were problems. And so working on Ubuntu is a lot simplifies, even if you cannot achieve that.
Yeah, it's true. I mean, it's. I mean, at the end, it's you spend a lot of time debugging. So you want to you want to put yourself in the most convenient situation for producing high quality code or enough quality code and functionalities. And you need the tools for debugging, for introspection,
Exactly.
for logging. So to do that in a soft real-time system with RT preempt in Linux or Ubuntu in general, it's much more easier for developers.
For developer, exactly. So if the quality of the real time provided is enough, then
Yeah, we have.
of
I mean,
course.
with this configuration, we have been able to have a system running at 4 kilohertz.
Uh-huh.
So it means that you have 4,000 times per second cycles. So
Yes, that's
it,
that's a lot, and you manage with that these Talos, human-sized humanoid robot, amazing. So yeah, that's the demonstration that it works.
but for instance, on the mobile base, you are enough with a 100 hertz control
Yeah.
cycle. Yeah. So in that case, soft real time is perfect. It's more than enough, and in the complexity, as you said before, for patching the kernel of the Linux, it's really well documented. It's easy to do, and it's affordable for everyone.
Great.
And
So
it's free. That is also
exactly.
yeah, because then QNX or other
Wow.
more they are really expensive, so they are out of reach for startups or for even hobbyists or robotics developer that want to have a simple system with a simple manipulator or simple mobile base working and respecting real-time constraints.
Great. And in any case, you mentioned Windows, right? Windows real time. No Windows.
I mean,
Yeah,
I've
not talking
seen
about.
no robots run. I've seen only one robot was running Windows that I think was Yubo.
Okay. Yes, the Korean one.
Yeah, they were using a special version of Windows with some kind of real-time capabilities. But I think that then it's not only the operating system, it's then also everything else that gets complicated. So I mean, if I had to imagine now, I know running all the ROS libraries and open source library that we commonly use in robotics in a Windows system, it would be really get complicated. Yeah.
Yes, yes, there's going to be a lot of extra work. Then, if we have this operating system real time layer already working, so I have my robot running this patch Ubuntu, then any program that I write on that computer is going to run in real time. Is that what it means? For example, let's say a ROS node that
Yeah.
is implementing the walking algorithm and publishing into the topic of the joints.
No, it's not. It's not that. Yeah. So you need
Okay.
to do something more. Yeah.
Okay.
So basically, by default, then every program that you execute will be scheduled by a generic scheduler that is not real-time safe or real-time capable. Yeah. So you to have a program being executed in as a real-time program, from one side you need to care that your program is real-time safe.
Okay. What does it mean?
So that means that if you have, for instance, I don't know, a loop for the computation of the algorithm, you need to care about not allocating memory in that loop, in that chunk of code, not using system calls that can create delay, latency. Even you should, let's say, be as much as predictable as possible. Yeah. So the code that you have there should be you should predict the amount of time that you need for that computation. It
Okay.
cannot vary from one execution to another. So
Okay.
this from one side. So the code, or at least part of the code. So if you imagine an application that has some, I don't know, configuration, initialization, then the
That's
loop, and then the, I don't know, some exit code in the application, only the part that is going to be executed many times should be
yes.
real-time safe.
The
Yeah?
control part, right?
Exactly, the control part. So your application, your code should be real-time ready.
Okay.
And then when you execute, when you configure the main thread and the threads that you want to have executed in real time, you need to specify which kind of scheduler you want to use,
Uh-huh.
and even the priority.
Okay. And how do you specify that? Is that in
There is
compilation time?
there is an API, yeah, and compilation time. You specify, okay, I want this is my main thread of the application, and you use some system calls in which you specify, I want to have this scheduler, and I want to have this priority in this scheduler.
Okay. Okay. And you put all that in the CMake, and then
Not in the CMake, you meet it in the code, yeah, in the code.
in the code itself.
Yeah.
Ah, okay. 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 Then okay.
No,
Then
it's at least from my knowledge, it's only possible in C++ and C code.
okay. And then also then that's another requirement. So we have to do this in C++ or C. Okay.
Yeah.
Yeah. Great. Then that's very interesting and important, because in most of the research centers, universities, they are using Python in order to simplify, even to work with ROS and so on. But in that case, in case that you need to do real time control, for that, you have to go to C++.
Yeah, I mean,
Great.
for prototyping, Python is great, but then if you want something, let's say, at production level, so that's something that is reliable, robust, and you need to migrate to a more powerful or adapt programming language
Correct.
that offer this kind of capabilities.
Yes, exactly. C++ is the perfect example, and also is the one supported by ROS. So if you're planning to work with ROS, then C++ is the best option for that kind of applications. Okay, then let me see. So, okay, so we have a program, any program, and then we have applied those constraints that you mentioned about the loop, taking care into the loop, and then indicating those specific schedulers and other stuff that we have to specify, and then it's running on real time. But does that apply to a ROS program? So if I write a ROS program, so how do I manage that? Because there is ROS control in there, right?
Yeah, I mean, yeah, that is a little bit even more in detail. So, yeah, our ROS program for me means that a node that
Yes.
use, I know, ROS interfaces for getting, I know, sensors or ROS topics
Information, yeah.
or services, action, and so in that sense, it's a little bit, let's say, you cannot use out of the shelf ROS subscribers and publisher in a real-time program. So what we do normally is that you can have in the same process multiple nodes. So
Okay.
you can have the ROS, let's say, layer, so the part of code that need to have access to topics or services can be run in a non-real-time thread,
Okay.
and then you can have some kind of synchronization with the main thread that is going to be executed in real time.
Okay, so wait a second. So the part that executes in real time is the one that performs the control, right? Is the one that computes based on the sensor data, computes the next action to take.
And that can be ROS agnostic, let's say.
Yeah. Okay. Yes.
Yeah, you don't need to have ROS messages inside the control code. Yeah.
Okay.
So you need to have input and output, and the algorithm for computing the control system. But then the communication with other nodes or other sensor, whatever, should be done in a different way if you want to do through ROS.
Okay.
And this is, as I always say before, this is a little bit what drove the need for ROS control.
Okay.
So was how could we get real-time control in ROS? So ROS control was a project initiated, I don't know, many years ago, like in 2012, 2013, I think, from Willow Garage in general, but then was more was designed initially for PR2 robot, and then was made more general by an effort shared with some other partners outside Willow Garage. We even from Pal Robotics we participated. So one of our colleagues, Adolfo Rodriguez, participated actively in the development of ROS control. And the idea of ROS control was to abstract from one side, to abstract the hardware so that you can think about an abstract representation of the resources that are available in a robot, so like sensor actuators in general, and to have controllers, so real-time controllers that can be reused and that can be easily tested both on a real robot and on in simulation. Yeah, so that was the idea on the design, but on which the design of ROS control was done. What does ROS control? Basically, it offers several packages and tools and libraries for real-time control. Okay. For instance, one is the controller manager, that is like a kind of scheduler of controllers, and this controller manager has one of its core part that is the one that is executed in real time.
Okay.
So you have the typical, let's say, structure of code in which you read the sensor, you execute the algorithm, and you write the commands.
Okay.
Okay. So this is done by ROS control, the controller manager that triggers all the updates of the controllers that are running, and then send the output commands to their actuators.
Exactly.
Yeah. And then there are out-of-the-shelf controllers that are coming with ROS control. So there are controllers just for publishing to ROS the state of the system. So you have a joint state publisher that publishes the TF and all the encoders readings, current readings from the models, so that then you can visualize the model on RVs. And that is done, for instance, with this duality, so that the joint state controller actually has two threads. So you have the part of the controller that is run in real time, that is ROS agnostic, I would say. But then you have a non-real-time thread that is the one that is publishing the topic of joint states.
Okay. Yeah. For any other ROS application that needs this.
Exactly. And this is possible also thanks to a package that is available in the ROS control family of tools. That is the real-time toolbox, in which you have the equivalent of the publishers typically used in ROS, but that are real-time safe.
Okay.
So you have real-time publishers, you have buffers for communicating from one thread to another, respecting real time, and so on and so forth.
Okay, and then so in this, okay, so there are a couple of things that are not clear to me there. One of them is about this sensors update that you mentioned that is not performed under the real-time loop. So the real-time program, a real-time. So that means also that then that we are not getting the latest results from the sensor. So
That's the point of ROS control. We eliminate this thanks to ROS control. So in ROS control,
yeah.
you have all the sensor and all actuators that are abstracted through the what is called robot hardware. So the ROS control core is what is a chunk of libraries and code that is talking to the hardware.
Okay.
And
Okay.
it's not at all ROS. It's
Okay.
simply, it actually depends on the robot.
Okay. Okay. Yeah.
So it's the one that every robotic developer that want to use ROS control should implement the
For
the
hardware
component,
interface.
the hardware interface that is talking to its hardware, depending on the communication interface, the driver of that hardware, and so on and so forth. And then on top of that, you have this standard hardware interface that allow to the controllers to connect through shared memory pointers to the sensor data and the commands to send to the actuators.
Data.
So that basically the core of the ROS control is not at all using neither topics or services.
Yeah, now makes sense. Now, okay, now it makes sense. Right. Okay, so that's perfect. Then I think that I understood that correctly. Now, and then the next question that is about the controllers that provide real time. You mentioned, hey, there is a lot of, well, there is not a lot, but
I mean, there are quite a bunch. Yeah,
Okay. So there are a lot of those controllers, and there is a special framework for creating those kind of controllers, which is called Orocos, right? Can you tell us what is Orocos and how enters into the picture?
Orocos can be seen as another middleware or it's a set of libraries, and the core of Orocos is the component library, so that Orocos is a component-based system, meaning that every component has some kind of life cycle management. So every ROS component is Orocos component. You have this init function, the config function, the update loop, and then the finish function, so that you can structure your code and the code of a component in a more elegant way, and you can divide what is going to be executed only once at the beginning, first time that you execute the component, what is going to be the configuration part of your component, so that if you want to reconfigure, changing some parameter, there is a set of lines of code that are the one responsible for that. There is then the update loop part of your component,
Which is the actual algorithm of control.
exactly.
Right?
And that, apart from that, Orocos what offers in intra-process communication, so that you can have real-time safe communication between components.
Yeah, that's amazing.
And also even better, and this is done through what in Orocos is called data ports or buffer ports. So that is another way to implement
Topics.
what in ROS is subscribers and publisher.
Yeah.
But what Orocos managed to do is that it is real-time safe.
Yeah, that's awesome.
The drawback of this, and that to achieve this, at least in the version of Orocos that we are using with this, everything should be in the same process. So the components are then executed in the same thread. So if you have a controller that is executed inside ROS control, and in our case, ROS control is a Orocos component, it means that everything is executed in the same thread.
Okay.
So this is good because you have then the real-time capabilities of the system. You can communicate between components with the buffer port, data ports, but then also has the drawback that one of the controllers blocks or fail, then all the system fail. Yeah. So this is the let's say the weak point of this system.
Okay.
So for give you a more general overview of what we are doing in our robot, we have this Orocos system that is in charge of deploying, let's say, the configuring the components that are loaded. So we have components, for instance, for talking to the hardware. So we have what we call actuators manager that is in charge of the communication of the main computer with the control board of every motor.
Okay.
But it is also in charge to, for instance, to read the state of the emergency button. It's in charge to read the IMU of the robot through serial interface. It's in charge to read the force torque sensor that are installed at the ankles or at the wrist of the robot that are connected through a different communication interface. So it's like let's say the main hardware driver is this actuators manager. Then the actuators manager communicates through data ports and buffer ports that are offered by Orocos to ROS control, that is another component of the Orocos system.
Okay.
And then inside the ROS control, we have the different controllers that are loaded dynamically. So you have position controllers, effort controllers, velocity controllers that are loaded dynamically and then can access the data that is coming from the hardware thanks to ROS control.
Awesome.
Yeah. And that outside Orocos, everything that is ROS is running. So ROS control offers this bridge from the Orocos world to the ROS world, and then you can have as many nodes you want that are running pure ROS and that can access topics or services that are provided by the controllers that are running ROS control.
Okay, okay, impressive. Then that means that your walking algorithms are executed in the Orocos part, right?
Yes, exactly.
But then the mobile-based navigation is running in the ROS part, which is not real-time control at that point. But if they need some information from the joint state, they are accessing through ROS control to this information of the joints
Yes.
that are the wheels, the status, and so on. Okay. Wow, awesome, impressive. That's impressive. Then I think that now we have the whole picture, right? We have the so everything that you need to do a real-time control system in ROS, right?
Yeah.
Now we have that, but we are talking so far about ROS 1. So all that is only for ROS 1. So far, only have talked about this. Then let me. The next question is about ROS 2. So what happens in ROS 2? Because ROS 2 is published, is advertised as who is able to do real-time control natively without having to do all these external access to external libraries or external systems that provide this real-time control to it in an, let's say, in an artificial way.
ROS 2 was designed taking into account the real-time needs of some robotics application. So the idea of ROS 2 is that they are relying on what is called DDS, so distributed data system that has a different way to communicate between processes and between threads. So the idea is that the DDS, there are implementations that are real-time safe, real-time ready of the DDS, and how ROS2 is designed and implemented is really, there are a lot of layers so that you can replace some of them and configure the system in a way that satisfy your needs. So for instance, you can easily use different implementation of DDS.
Okay.
So select out of the shelf DDS libraries, you can test them and you can see the one that are better for your system in terms of performance, in terms of real-time readiness and latency, jitter, and much more. So let's say that it's much more complicated in terms of architecture ROS 2 compared to ROS 1. And so from this composition of layers in which the client library, so the C++ libraries API that you use for your program then attacks a layer that is called ROS client library that is common among all the different programming language that you are gonna use. So there are then, you can even use Java, you can use, I don't know, Ruby, whatever, but the underlying client libraries of ROS won't change.
Okay.
So they offer like this decoupling from the language used by the user and the underlying middleware calls that the system is then using. Then you have this middleware layer in which you have this abstraction from the communication libraries that are used
Okay.
for passing messages from one application to another. And
Okay.
in this sense, DDS is something that is much more powerful than TCP/IP and UDP that was the main transport system used in ROS1.
Mhm.
And then there is also much more flexibilities in terms of configurability of the communication layer. So in terms of quality of service, you can configure much more parameters.
Yes, like security also.
Exactly, security, encryption, and so that are more suitable for then, I know, delivering software products that are industrial quality ready.
Okay, okay. Then I don't understand now if we need then to use ROS control in that ROS2 system, because what would be the role then of ROS2 in that?
I mean,
Of ROS control, I mean.
ROS2 control will be different from ROS control. So what we probably the new ROS node in ROS2 are similar to what are the components in Orocos. So a node could be a component, and you have also the similar functionalities in terms of a component life
Yes,
cycle.
life
So you have
cycles,
this
exactly.
structure of a node with different function that need to be defined by
Defined.
the user, so that you can isolate what is going to be initialization code from what is going to be control code from what is going to be code that only is executed when a node is terminated.
Uh-huh.
So there is this, let's say, functionality that are going to be present in ROS2. And from the other side, having a node that is a component means that you can have then a composition of components. So something similar to what Orocos is doing. Yeah, the components in Orocos that then they are scheduled and then they are communicated between them with real-time safe communication layers. You could have also in ROS2, because you then can create what is called executor
Uh-huh.
that can
Okay.
be seen as a controller manager in ROS1 or Orocos scheduler in our system. So in which you have different ROS2 nodes that are executed based on some kind of timer or scheduling policy.
Constraints. Yeah.
Then if you can have a DDS system that communicates in between the components with real-time safe capabilities, at the end you have the same system that we have in ROS1 with Orocos, ROS
I
control,
see.
and so on and so forth.
I see, I see. I see, okay. Okay, still not very clear about the ROS2 control package role inside ROS2, but I don't want to ask.
At the end, what we are trying to do, because we are even involved in a European project, it's called from Rosin. There was this opportunity for getting funding for the migration of ROS control to ROS2.
Yes,
And,
yes,
and we are actively participating in that. Actually, we are close to the first milestone of the project,
yeah.
and so the idea is that we want to reuse or migrate the controllers that are in ROS1 and that they are stable, that are working fine, to ROS2.
Uh-huh.
So there is already a lot of code that is working, that is worth migrating to ROS2, because otherwise we need to rewrite from scratch position controllers, joint state publisher, and we don't want to do that. Yeah.
Yeah.
So the idea is to provide a set of controllers that are gonna work out of the box to people that is gonna use only ROS2.
There's two. Okay. Okay.
So if you have a robot that is pure ROS2, how will you do position control of a joint? Yeah. So the idea of ROS2 control is to provide these building blocks
Uh-huh.
and to make then the controllers up, let's say, agnostic from simulation or
Real.
the real hardware. So you have all this. You have a controller manager that is scheduling and loading, unloading the controller. So you still need these functionalities. They are going to be different because they are going to benefit from the new architecture of ROS2. And so the idea is to provide a solution without having everybody reinventing the wheel
All
every
the
time.
time. All the time. Okay, yeah. So I don't want to ask you more about ROS2 control because so I knew that Pal Robotics is involved, but and the leader of the ROS package so far, if I have understood, is Bente.
Yes, yes, yes.
So Bente, for those who doesn't know, he is he was a colleague of us. So we were working all three together at Pal Robotics, and now he's working in at the University of I don't remember now. So anyway, I have a schedule already an interview with Bente in 2 weeks, so in 2 episodes.
Oh, nice. You can have a clear picture of what
Exactly. So I don't want you to explain everything. So then the audience is going to just not listen to the episode of Bente explaining about specifically about ROS2 control. So
yeah, for sure we'll have much more details than what I did, what I say. So
okay.
don't miss
Great.
the episode.
Okay, exactly. Okay. And then final question. So are you planning to move your bipeds into ROS2 in the short term?
Nice question and difficult answer. Because the problem for us is that to migrate all the amount of code that we have to ROS2, it's a huge amount of work, really huge amount of work. So, and especially is not only the ROS control part and the controller, but there are a lot of libraries that need to be adapted and migrated. So it's really what we are, for the moment, what we are targeting is for the next year to have coexistence of ROS1 and ROS2 in some of our platforms, so to allow people that have native ROS2 application to be executed on the robot to develop ROS2 nodes for our robot that at the end we want to provide a research platform and so to give the possibility to the researcher to use the latest libraries for ROS2 is something that we are really trying to do as soon as possible. At the same time, we are really interested, for instance, in new developments in navigation stack. So that the navigation tool looks much more flexible and powerful than the navigation stack in ROS1. So probably and that can be some kind of let's say, I would say not easily, but at least it's not that dramatic, the adoption of the navigation in ROS2 without, completely changing the thing.
whole-
Because at the end, yeah, because navigation, you can see navigation as a black box in which you have sensory inputs and commands outputs.
Yeah.
And in that sense, you can even have only the navigation running in ROS2 and all your system in ROS1, and then use an ROS2 bridge to ROS1, so that you can have this hybrid system.
Exactly. I was going to recommend you exactly that, so you don't have to transfer your whole robot from ROS1 into ROS2 at once.
Yeah,
So you
exactly.
can select, for example, one node. Let's say one node, only one. Then you have your system on ROS1 here, and then you put here the ROS1 bridge. The ROS1 bridge is the package that manages communication between a ROS1 system and a ROS2 system. Okay, then you put here the bridge, and then you take one of the nodes from here, and then you remove from here and put it in ROS2 world, and publish the same data that he was generating in ROS1, you publish through the ROS bridge. So all your programs still working can access that data. And so you can do a progressive transition from the ROS1 to ROS2. And also any new thing that you are going to develop, you can do it directly in ROS2 already, and then progressively. But it's very interesting, this view that you mentioned about. It's a lot of work to transfer from one to the other, because you are a company, very important company in the robotics world, about that is building robots based on ROS, and there exists this problem of adoption of ROS2, but especially by companies, right? Because the new people that come to the ROS world, they want to learn ROS2. They say, oh, ROS2, yeah, because what is the last one? What is the best one? The last one, this one. So they go for that. That's right. But for all the other people that is already there, that have built products, so that's difficult. It's a lot of work, and it's going to take several years, right?
Yeah, it's going to take much more time, and especially still not all the functionality that we have in ROS 1
Yeah.
are available in ROS 2. I mean, no, Action Leap or no.
Action Leap is already there.
Okay, nice. Okay.
Yes, from Eloquent.
Yeah, but so I don't know. There are still some I don't know.
Yeah.
It means a lot of
Cross control. Cross
yeah,
control is not there.
yeah. And we will have a demonstration of a mobile base with a diff drive controller of ROS2 control. Sometime soon, I think beginning of December, there is a ROS in Industrial conference.
I'll be there also.
We will present our result with this demo with a mobile base and the ROS2 control running a diff drive controller.
Great. Okay, so I will be attentive, because I will also be attending there and presenting about also at the conference. Do you mean the one in December, right?
Yes,
ROS Industrial in December, right? Okay, great. Okay, great. So I think that's all for today. We covered a lot of topics, but I think that it was a very clear picture about how to do now people, if they want to implement a real-time system in ROS, they have to dig deeper. But this picture about what is needed and the path to follow, I think it's very clear stated by you here. So thank you very much, Luca. Thank you.
It's been a pleasure. Thank you for the opportunity, Ricardo. It's always a pleasure.
Thank you. And that is all for today. So before finishing, I would like to thank you, all the listeners there, for listening to the podcast. And I would like you to recommend the podcast to your colleagues. So please share it, because we want to reach more people. We want to inform more people, more ROS developers about the latest subjects in ROS, in the ROS world. So for that, we need your help. So if you are listening to this and you like the podcast, help us on that, please. So that's all for today. And so we are going to meet next week with another lesson from the experts. And until then, keep pushing your ROS learning.